In the 10 series coherence gating experiments, we tested 6 distinct chaotic systems to evaluate structural coupling. Out of those 6, only the Lorenz system locked in. The remaining 5 systems, including Rossler and Chouet, yielded predominantly effective damping classifications. They failed to cross the engagement threshold and did not couple. This leaves a specific analytical question. Why did these digital attractors resist coherence gating? The anomaly does not exist within the geometry of the chaotic systems themselves. The failure stems directly from the mathematical nature of the probe used to test them. The 10 series outcomes represent a precise measurement of the limits inherent to scalar limit probing. Throughout those experiments, the primary mathematical tool was the broad-spectrum Gaussian coherence kernel. This equation reveals the exact limitation. The mathematical structure of this Gaussian kernel is identical to a Maxwell-Boltzmann distribution. This functional form creates a thermal coherence spread. It distributes energy statistically across all spatial configurations. Because of this wide spread, only a tiny fraction of the coherence overlaps with the optimal dynamical cross-section. Compare that statistical spread to the theoretical ideal, a directed, monoenergetic spike. This targets the optimal state precisely, concentrating energy rather than diffusing it. Applying a Gaussian kernel to geometric attractors is mathematically equivalent to heating them with thermal noise. This statistical dilution explains the pervasive damping recorded throughout the 10 series. This inefficiency maps precisely to established macroscopic physics, specifically the mechanics of tokamak fusion reactors. Tokamaks rely entirely on thermal equilibrium confinement. Because energy follows a Maxwellian distribution, only a microscopic fraction of plasma particles reside within the optimal fusion energy cross-section at any given moment. The alternative approach in plasma physics abandons thermal equilibrium entirely, utilizing field-reversed configurations and colliding beam reactors. These FRC systems use directed beam injection for non-Maxwellian monoenergetic confinement. By doing so, almost all particles sit at the exact required energy state simultaneously. To achieve structural coupling, our coherence mathematics must replicate this transition. We have to move away from tokamak-style thermal spreading and develop FRC-style directed beams. Generating this directed coherence is mathematically impossible using simple scalar fields. It forces the theoretical framework to undergo a strict bifurcation at C equals 2. When two distinct spin 1/2 recursions pair up to form helium, the composite system accesses two distinct mathematical pathways. The first pathway is the singlet channel, labeled S equals 0. This state is entirely antisymmetric under exchange. The singlet channel runs on standard scalar addition. It aggregates individual phase streams into a single number. This scalar averaging mechanism shares an exact physical analog with bosonic pairs in superfluid helium-4. Helium-4 particles are indistinguishable from one another. They average out their internal states, meaning they operate entirely within the Maxwellian thermal limit. The singlet channel provides the math required to describe closed-shell identity attractors, but the operation itself destroys the phase data required for directed coherence. The second mathematical pathway is the triplet, or spinor channel, labeled S equals 1. Here, the structure requires a 2x2 matrix. This channel utilizes Pauli matrices. These mathematical operators encode phase exchange, circulation, and asymmetry. The defining property of Pauli matrix algebra is non-commutativity. Non-commutativity mathematically prevents phase averaging. The exact sequence of interaction between the two recursions is permanently recorded. This matrix formulation mirrors physical reality. It is the exact math used to map the spin-orbital coupling of fermionic pairing in superfluid helium-3. Operating in the spinor channel provides the precise architecture to engineer directed non-Maxwellian coherence, because it ensures structural memory is never lost to averaging. Transitioning from the scalar to the spinor channel rewrites the topological rules of the system. This comparison shows the difference. The scalar channel provides U1 topological protection, which strictly limits the system to integer vortex charges. The spinor channel acquires an additional SO3 factor. This permits half-integer vortex charges, requiring a continuous 720-degree phase winding to complete an identity return. These topological properties physically protect phase memory, establishing the operational constraints required to build physical hardware that utilizes non-Maxwellian coupling. The 20 series experimental program takes this out of simulation. We are replacing digital attractors with physical mechanisms to validate the Spinor channel in the laboratory. The apparatus chosen for this translation relies on macroscopic Chladni plates. Driving these plates at distinct acoustic frequencies produces highly specific, measurable standing wave structures. This equation defines mode degeneracy. This state occurs when two flipped coordinate modes, such as the 1-2 pattern and the 2-1 pattern, resonate at the exact same frequency. These degenerate pairs allow us to form two analog superpositions, a symmetric combination that serves as our scalar analog, and an antisymmetric combination that serves as our Spinor analog. Degenerate acoustic modes give us a fully testable macroscopic two-state system. With it, we can directly observe the bifurcation between thermal and directed coherence regimes. Based on this mapping, we can state our experimental predictions, beginning with the Maxwellian limit. Applying broadband Gaussian coherence gating to the plate will fail to select a specific mode. This will produce random, unpredictable shifting between the symmetric and antisymmetric states. The contrasting prediction isolates the non-Maxwellian limit. Utilizing a single frequency drive with precise subharmonic coherence gating will systematically break the degeneracy. The system will be forced into a locked antisymmetric symmetry. Addendum 20.0 strictly establishes the predictive mathematics. Empirical validation using these frequencies is reserved for the upcoming physical trials. Engineering this macroscopic mode selection proves the existence of the Spinor channel, resolving the thermal inefficiency problem to enable structural coupling in complex dynamics.